Hello everybody, and welcome to our video on implicit differentiation. So implicit differentiation is really nothing new or different than what we've been doing. We've been dealing with derivatives, we've been dealing with chain rules. So up to this point, our approaches have only offered the ability to analyze functions that we can solve explicitly for x. So now we're going to consider the problem of taking derivatives for functions which cannot be written explicitly in terms of x, as well as equations which are not actually functions. So the first thing we're going to do is investigate derivatives related to the equation x squared plus y squared equals 1. So first of all, let's take a look at the graph of this. This is the equation of the unit circle. So the circle with radius 1 centered at 0, 0. And of course, this doesn't pass the vertical line test. It is not a function. So that means that we can't directly take derivatives for this thing. But what we can do is solve for two functions instead. So if I do a little rearranging here, I can write y squared equals 1 minus x squared. And then when I take the square root, I get y equals plus or minus the square root of 1 minus x squared. So now I have two different functions. We'll call one of these y1, the positive square root. And we'll call the other y2, the negative square root. So if we take a look, we'll just highlight these here. y1 here is the positive square root. It tells us it's the positive y values of the circle. And y2 that's the negative square root, so it's the negative y values of the circle. And you can see that each of these individually is a function. Now I'm going to rewrite these slightly further as being to the 1/2 power. So this will be negative 1 minus x squared to the 1/2 power. And then I'm going to take the derivative using the chain rule. So I'm going to kind of skip a little bit of work here. I'm not going to write out all of my chain rule explicitly, but remember this is like my u, so I get the derivative of this with respect to u. So that's 1/2 u to the negative 1/2 power times, and then what do I get outside? Well, the derivative of u. The derivative of u is negative 2x. So the 2's cancel, and I get left with negative x times 1 minus x squared to the negative 1/2. And this will be negative x over the square root of 1 minus x squared. Now, I could do all the same work for y2, but these two functions differ only by the constant multiple negative 1, so their derivatives will be opposites. This is negative x over the square root, so the negative of that becomes positive. So I'll just skip a little bit of that work there. So of course we could start plugging in x values and we would see, we would be able to calculate the tangents here. It should make sense that these answers are negatives of one another because of course if I plot a tangent line here, let's do this in red. If I plot a tangent line here, and if I use the same x value but I go up here, I'm going to get the tangent line that has the negative of that slope, right? They're going to otherwise be the same, but with negative slopes of each other. Okay, so that's how we would calculate the derivatives for each of these individual functions. But perhaps we had a function where we couldn't solve explicitly for y equals a function of x, like that. Now that's obviously not the case here, but we're going to tackle this problem, but treating it as if we were not able to do that. So now we're going to be looking at the equation x squared plus y squared equals 1. And we're going to use derivatives as operators to manipulate this equation. So we're going to first touch on a few little things here. So one of the things that we're assuming here is that y is a function of x, that y is dependent on x. Now, even though this isn't strictly a function, there are multiple functions defined within here. We are still considering y as a variable being dependent on the values of x. So what that means is that when I take a derivative of y, right, I just express it as dy dx. Because I'm taking that derivative with respect to x, and I don't actually know what y is. On the other hand, when I take the derivative of x with respect to x, well, that's just 1. So I'm going to write this out the first time a little unnecessarily verbose, perhaps, to make things as clear as possible. And then when we do future problems, we'll cut down on a little bit of the extras here. So what I'm going to do is take the derivative with respect to x of both sides of the equation. And of course, I can split this derivative up into the derivative of x squared plus the derivative of y squared. And the derivative of 1 is just 0, so I'll go ahead and write that now. Now, the derivative of x squared with respect to x is 2x. Now, I don't need to write this, and we never normally would, but I think it'll help make clear what's happening here. See, this is a function, and the chain rule always applies to these inner functions. So my inner function here is x, so I'm taking the derivative of x with respect to x, which is 1. So we normally don't bother ever writing that, but it's always there implicitly, so to speak. But when we look at the y squared and we take that derivative, we get 2y times, now we're treating y as a variable dependent on x, so we have to apply the chain rule here and write dy dx. But again, of course, this dx is just 1, right? So there's not much point in actually writing it that way. So we won't normally write it that way in the future. We'll just go ahead and finish writing that for this particular example. So we replace this with 1, we get 2x plus 2y times dy dx. So I want the derivative of y with respect to x. So I'm just going to solve this thing for dy dx. Okay, well, I move the 2x over. I get 2y dy dx. So all I'm doing is just solving this algebraically like I would solve for any missing variable in an algebra equation, right? I want to solve for this, so I isolate it to one side. I divide by 2y, and I get dy dx equals negative x divided by y. So this is my implicit derivative. Now, this seems a whole lot different than the previous formula, but it's actually not. If you take a look at the previous formula, we had negative x over the square root of this, but what is y? Y is the square root of 1 minus x squared. It's the same thing. And in this case, y was negative that square root, so negative x over the negative of the square root, and the negatives cancel. So you get the same thing, and you'll get the same values for the slopes of the tangent lines. But the difference is that when using this implicit differentiation form here, you would need to know both the x and y value of the point, because there are 2 points that share the same x value on this circle. So if I'm looking at one equation for the derivatives related, or the slopes of tangent lines related to the whole circle, then I have to illustrate which specific point I'm using by putting the values for both x and y in place. So hopefully that makes some amount of sense here. It's a little bit of a tricky topic, but it's not too bad. Basically, the strategy for implicit differentiation is take derivatives of both sides of the equation, and then once you've done that, solve algebraically for whatever dy dx you have. And once you've solved algebraically, you're done. So let's go ahead and just tackle a few more examples of this. So we're going to take the derivative of both sides of the equation with respect to x. And again, I'm going to kind of split these up piece by piece here. Really want to break down every little step at first while we're getting used to this. So first I'm splitting up my sum. And notice, this is another case where the Leibniz notation is really helpful because it indicates what variable we're differentiating with respect to. And now we've got two variables at play in our equations. This helps me keep in mind that I have to treat y as some function of x, that I just don't know what it is. That way I make sure to apply the chain rule when I need to. So when I look here, the derivative of y to the 5th dx, I have to apply the chain rule. I get 5y to the 4th times whatever the derivative of y with respect to x would be. Plus. Now here, I'm going to go ahead and switch to, well, this is a product rule. I'm not going to switch anything. I'll keep in Leibniz notation for this. But this is the product rule because I have a product of two functions here. So I'll take the derivative with respect to x of x squared times y cubed plus x squared times the derivative with respect to x of y cubed equals. Now the derivative of 1 is just 0 plus, and here again we have a product, so we take the derivative with respect to x of x to the 4th times y plus x to the 4th times the derivative of y with respect to x. So now let's just go ahead and compute a few more of these derivatives here. We're starting to get somewhere. 5y to the 4th dy dx plus the derivative of x squared, that's 2x times the y cubed here, plus x squared times, and the derivative of y cubed, we get 3y squared, but again, we're taking the derivative with respect to x, so we need to apply the chain rule. We multiply by dy dx equals, and here we get 4x cubed times y plus x to the 4th times dy dx. So really we've done the hardest part here. So now what we got to think about is we're trying to solve for dy dx. So remember, this is just algebra. Don't overthink it. All we're going to do is move all of the dy dx to one side of the equation, move everything else to the other side of the equation, and solve this like any old algebra variable. So we'll start by rewriting what's already on the left-hand side. I'm just going to rewrite this slightly and put the 3 in front. 3x squared y squared dy dx. And here, when I take this term and move it to this side of the equation, I've got to subtract it. And now I got to take this middle term here and move it to the right side. So I get 4x cubed times y minus 2xy cubed. And we're doing pretty good here. So the next step, I'm going to factor out dy dx. And I get 5y to the 4th plus 3x squared y squared minus x to the 4th. And times the dy equals 4x cubed y minus 2xy cubed. And finally, I'm just going to divide this thing that's multiplying by dy dx. So I've now fully isolated dy dx, and I get 4x cubed y minus 2xy cubed over 5y to the fourth plus 3x squared y squared minus x to the fourth. Okay, so that's it. That's our implicit derivative formula for that function. So again, if you're careful and you're writing out each step of your derivatives, none of the derivatives are hard to take in these problems, but you do have to do a little bit of careful algebraic solving at the end. All right, so let's go ahead and move on to example 3 here. So same process. I'm going to take the derivative with respect to x of both sides of the equation. And I'm going to write a little bit quicker just because, hey, this is now our third example. We're kind of seeing how this all goes. So both of these are products. I need to apply the product rule. I take the derivative with respect to x of y times sine of x squared plus y times the derivative with respect to x of sine of x squared equals the derivative with respect to x of x times sine of y squared plus x times the derivative with respect to x of sine of y squared. Okay, the derivative of y with respect to x, well, that's still just dy dx because we don't know what it is. Plus y times. Now here I've got to apply a chain rule. And this is, we think of sine of u, so the derivative is cosine of u, but I'm going to skip straight to writing cosine of x squared times the derivative of u, which is 2x in this case. So I'm skipping that little chain rule derivative here. Derivative of x with respect to x is 1. And we have another chain rule problem here. So we get the derivative of sine, that's cosine of u, which is y squared, times the derivative of u, which is 2y. But remember, y is also a function of x, so I need to apply the chain rule there. So I got to multiply by dy dx. And now, again, this just becomes an algebra problem. Anywhere you see a dy dx, you need to move that all to one side of the equation and solve for it. So we get dy dx times sine of x squared minus, and I'm going to rewrite this slightly. I'll put the dy dx in front times 2xy cosine of y squared, just looks a little more symmetric there, equals sine of y squared. That's this guy here, minus this guy. Minus, and again, I'm going to rewrite it slightly, 2xy cosine of x squared. So now I factor out my dy dx. I get dy dx times sine of x squared minus 2xy cosine of y squared equals sine of y squared minus 2xy cosine of x squared. And I divide this factor across, and finally I get dy dx equals sine of y squared minus 2xy cosine of x squared over sine of x squared minus 2xy cosine of y squared. All right, well, that's it for that problem. Let's go ahead and move on forward. So here we've been asked for the second derivative of y with respect to x twice. So we're going to start out just finding the first derivative the same way we've been doing. So we take the derivative with respect to x of both sides of the equation. And now that we've done a few of these, I'm going to start skipping a few more steps here. So the derivative of x to the fourth is going to be 4x cubed plus 4y cubed times dy dx equals the derivative of 16, which is 0. I move the 4x cubed across. That gives me 4y cubed dy dx equals negative 4x cubed. And I divide the 4y cubed across, and I get dy dx equals negative x cubed over y cubed. Okay, so now when I take my second derivative, it's a little bit easier to deal with because I'm just taking the derivative of the first derivative So here we just apply the quotient rule. So we get the low d high y cubed times the derivative with respect to x of negative x cubed minus high d low, that's negative x cubed times the derivative with respect to x of y cubed divided by low squared. This gives me y cubed times negative 3x squared minus a negative, which becomes positive, x cubed times 3y squared times dy dx all over y to the 6th, right? That's a y cubed squared. And actually, let me just move that over to the left here a little bit, give myself slightly more room. Now that might seem like, oh no, our derivative has got dy dx in it still. What are we going to do? But remember, we already know what dy dx is, so we can just plug that right back into there. So rewriting this a little cleaner, we get a negative 3x squared y cubed plus 3x cubed y squared times negative x cubed over y cubed divided by y to the 6th. So this can be simplified fairly easily. You could split this fraction up into two, simplify each part a little bit, and it'll clean up nicely. I'm going to go ahead and skip that part and just leave this as is. Leave that part to the viewer. Okay, so let's go ahead and move on to the next example. So here we're going to find the equation of a tangent line to this hyperbola at the point 1, 2. So remember a hyperbola, it sort of looks like a parabola, but there's a symmetric side to it. And it could be facing vertically, or a hyperbola could be facing horizontally, right? Now we're not going to manipulate this equation into a form where we could determine the shape of the hyperbola. We're just going to dive right in and do the implicit differentiation part. So let's go ahead and take the derivative here, because if we want to find the tangent line, we've got to first find the derivative, or so we can find the slope at that point. So we take the derivative with respect to x of both sides of the equation. Okay, so take the derivative of both sides of the equation. Now, we're going to write this one a little carefully because we got a product in here and we don't want to make a silly mistake. So the derivative of x squared is 2x plus, and we've got 2 times xy, And this is a product of two functions. This is a constant multiple, so we can pull that in front. And then we need to use our product rule for this. dx times y plus x times dy dx. Minus 2y dy dx plus the derivative of x with respect to itself equals 0. Okay, so here we get 2x plus 2 times 1 times y, that's y, plus x times dy dx. Minus 2y times dy dx plus 1 equals 0. Okay, so let's go ahead and distribute this stuff here. We get 2x plus 2y plus 2x times dy dx minus 2y times dy dx plus 1 equals 0. And now we're at the stage where we just solve for dy dx. So we'll leave the 2x dy dx minus the 2y dy dx on this side of the equation. And we'll move everything else across, and we get a negative 1 minus 2x minus 2y. Now here I'm going to skip a little step. I'm going to factor out dy dx, and then I'm going to divide by the 2x minus 2y. So I get negative 1 minus 2x minus 2y over 2x minus 2y. Okay, so if I want this derivative at the point 1, 2, then the derivative will be negative 1 minus 2 times 1 minus 2 times 2 over 2 times 1 minus 2 times 2. So this is negative 1 minus 2, that's negative 3 minus 4, that's negative 7 over 2 minus 4, that's negative 2. So this is 7 halves. I perhaps should have given myself a little more space to work with, but I'll go ahead and finish the tangent line part here. Because all we need is y equals f prime of 1. Well, let's just write m, because technically this is not a function. Y equals m times x minus 1 plus 2. That's my x value 1 and my y value 2. And so my slope, m, is just 7 halves. So y equals 7x over 2 minus 7 halves plus 2. 2 is 4 halves. So this is 7x over 2 minus 3 halves. Okay, so that's it for that one, and we're going to finish this up with a nice easy problem. Use implicit differentiation to find the derivative of y equals secant inverse of x. So previously, when we were investigating inverse functions, we had to use the inverse derivative theorem to find all of those derivative formulas. But now that we have the tools of implicit differentiation, we can go back and rederive all of those derivatives that we previously used the inverse function theorem for. We can now use an approach for with implicit differentiation. So I'm going to demonstrate that approach here on this one example with secant inverse, and you can take this example and apply it to the other trig inverse functions, etc. If you want an easier way to, say, derive these formulas in case you forgot them. So how do we do that? Well, these are inverse functions, so they switch inputs and outputs. So I'm going to look at secant of y equal to x. Then I'm going to take the derivative with respect to x of both sides of the equation. And that's going to give me, well, the derivative of secant is going to be secant of y times tangent of y. But we're taking the derivative with respect to x here. So we've got to apply the chain rule, which gives us a dy dx equals, and the derivative of x is just 1. So if I divide secant y tangent y, I get dy dx equals 1 over secant of y tangent of y. Now, that's not the formula that we know, but we can get that by just doing a little bit of extra manipulation. First of all, we know secant of y equals x, so we could substitute that. But we can also say, hey, y here is an angle. It's the input of a trig function, so it must be an angle. And if secant of y equals x, well, that's the same thing as saying cosine of y is 1 over x. So that's adjacent over hypotenuse. And so if I solve for this other side, z squared plus 1 squared equals x squared, I get z equals the square root of x squared minus 1. So that tells me that tangent of y is equal to opposite over adjacent, which is just the square root of x squared minus 1. So now I can plug those two things in. Secant of y is x. Tangent of y is the square root of x squared minus 1. So that just gives us a different approach to find our derivative for secant inverse. And again, this is really useful if you happen to have forgotten your inverse trig derivatives. Say you're on a test and you're like, uh-oh, I forgot what cosecant inverse's derivative was. Well, then you can use implicit differentiation, and as long as you know the derivative for cosecant, you should be able to work through this process and figure out the inverse derivative. Okay, well, hopefully that was helpful. Thank you for watching. Have a great day.